Hello, everybody. Good morning, good afternoon, or good evening. Thanks for tuning to, the Water Academy channel. These WAVE webinars have been a hit for sure, and the responsible for this fantastic engagement is our presenter, Garth Parker Jr., and the subject matter experts that he brings along to each of these sessions. Today, Garth and his guests will take you through a deep dive into Dupont's water application, Value Engine, WAVE software, focusing on ION EXCHANGE RESINS. We hope you enjoy this free webinar program and make the most of our engagement tools by downloading your certification of attendance, making questions, and always sharing your feedback with us. Okay, so now let's take a look in the school icons going on in your dashboard. You can access all engagement resources from the bottom of your screen by simply clicking on the colored icon, or you can resize or move them around as you wish to best fit your screen size. This is a deep dive, so you may already have the program, but for those who are interested, you can find a link to download WAVE in the resource list, or there is just a big banner in your dashboard that can take you there as well. And talking about that, please help us understand if you already have the program by answering the poll question that just popped up in your slide window. So let's see what we got here. Okay, give you a minute to respond, yes, no, or you plan to download after this webinar in case you don't have it.
Oh, okay.
Okay, so you see the majority of you do have, and you can, as I said, you can always download it right now. So we'd appreciate from you the best way to raise your questions, hear your comments, in the purple Q&A box in the lower left corner. And if your question is longer and you'd like to have a more personal response afterwards, you can do that with the blue Contact Us button. But please do submit your questions throughout the webinar. We'll have more experts than the ones you see here in the webcam in the background, just working to give you prompt responses. And they are nothing less than Bill Carlin and Mark Flatt. So thanks for also helping us today, Bill and Mark.
Thanks,
so
guys.
Matt Roth and Donna DeFlavors Murphy will also be selecting some questions to discuss with Garth in the final Q&A session. So don't be shy, we have a strong group of experts available just for you. To get your certificate of attendance, that includes PDH credits, you just need to make for the first 30 minutes of this webinar, and then it will become available for download in the dashboard. Know that this presentation is being recorded for on-demand view, so you can always come back to the content and refer to your colleagues. Finally, don't forget to check out the resource folder, as many relevant materials were placed there for you, including the link to register for all webinars as part of the WAVE series. Now back to our topic, and I'm happy to introduce our speakers. Garth Parker is a research scientist in the Technical Service and Development Group of Dupont Water Solutions, based in Philadelphia, United States. He has worked for 32 years for Rohm and Haas, Dow, Chemical, and Dupont, primarily in applications development and modeling of water treatment technologies. He has been the technical leader of the WAVE development team since the project's inception, so he's WAVE's father. Garth has a PhD in chemical physics from the California Institute of Technology. And today, two of our ION EXCHANGE senior engineers will be supporting Garth by bringing relevant questions from you to him, and they are Matt Roth, Technical Service Manager supporting membrane and ION EXCHANGE product lines for Dupont Water Solutions in North America, and Donna DeFlavors Murphy, Senior Technical Service and Development for Dupont Water Solutions, being her field of expertise, ION EXCHANGE in industrial water applications. So welcome, everyone, and I'll leave you now with this amazing team. Garth, the stage is all yours to fire up that WAVE engine.
Okay, thank you, everybody. I believe, Matt, you're up first. Let me start sharing my screen so everyone can see WAVE.
Hi, everyone. All right, so Garth, okay, so very nice. All right, so hi, everyone. It's good to be here. Thank you for joining us. I just want to say hello, and I'm excited about this. I have been working with Garth as part of his ION EXCHANGE, what we call the SWAT team, for the past roughly 5 years. I use WAVE all the time, so I'm excited about this. So, okay, Garth, I am seeing your screen, and For this first example that we talked about running through, I wanted to start with something initially simple and then explore some of the features of Wave that are maybe a little lesser known or a little deeper into the capabilities of the program. And we're just going to start with a ion exchange softener with a feed water flow rate that I have as 462.5 GPM.
Okay, so the first thing let's flip the units over. Let's use US units, and we'll go degree C and BVs and H.
Yes.
Okay, so those are now the units for this design, and you said you wanted a flow of
462.5.
Okay, so your feed water.
Yeah, and I sent over ahead of time a feed water for us to use for this example, I think.
So we will open it from our library. So you can store waters in the library and use them at other times, which is very convenient when you want to share waters and projects with other people. Okay. So now we'll move on to the ion exchange softener, and this is going to be a sodium form SAC resin softener, so you would select that one down here in the bottom right corner.
Okay, and in this particular case, we were requested to start with a 24-hour target throughput. And when I get to this screen, I always, for a new plant design, my typical approach is to do, I see there's a lot of options on this page, but I start with, we're doing a new plant design, which we have selected, and for train configuration, I do one online and one in standby in most cases. And we are going to look at that feature a little bit more after we get through our base design, but for now, let's start with a one on and one in standby. And since we know in this case we were asked for 24 hours of throughput, let's start with that, but we'll also take a look at the specific velocity feature in a little bit.
Okay. So moving on, after filling out the initialization screen, you would go to the vessel screen. Since we're doing a SAC softener, there's only one possible vessel. It's a SAC. And what kind of regeneration system would you like?
We're going to do co-flow here, co-current.
Co-current. And you should get a little diagram here that matches your design. Confirm you got it correct.
All right.
Next, you step through to the resin. And you would like...
In this case, I'd like to stay with the HPR 1100 NA.
Okay. And then we step through to the regeneration conditions. Right. Being a softener, it's going to be just plain salt. Mm-hmm. It will auto-populate the default concentration and 100% at that concentration, and the product quality that you're looking for.
All right. So in this case, we were asked for 5 ppm SCaCO3 on average and a 10 ppm endpoint.
And put those. Okay.
Yep, and I was hoping to start with a dose of 10 pounds per cubic foot. And in this particular example that I'm pulling from, the customer asked for a 0.9 safety factor. So I thought we could do that as well. And so we're moving relatively quick through this design to get to our initial pass of the design, so we can look at a few of the parameters that were noted as important for this specific case. And one of them is pressure drop. But first, let's just get to look at this and see how the design works. So we have our summary report and system recovery of 95.7%. All right.
Yep.
And then do you mind scrolling down, Garth, just to look at pressure drop? One of the things that we had noted from this design, and I think this is where we're going to get into one of our first deeper features, is that there's a stipulation that across the full feed water temperature range, we would not exceed a pressure drop of 20 psi. And in this case, at the design case, we're seeing a pressure drop. And if you don't mind just pulling your mouse down there, at the design case, we're seeing a pressure drop of about 12.3. PSI. But before we move forward, do you just want to see if we have any warnings for this base design?
No, we had no warnings here.
Okay. So now one of the features we want to show is that we can take this design and change the evaluation of this design, frozen as it is, at a given temperature or at the minimum temperature in our that we had in our feed water. And in this case, the minimum temperature is already pretty low. It was about 5C, so we could either put that select minimum up there or specify the 5C and then refresh the report, and we can quickly look at what the pressure drop estimate is in this case. All right, so as you scroll down, I would expect, Garth, that we'd see some shift in the...
Yeah.
Can you just select...
we tripped the bug.
Okay.
Developmental version. And,
okay. So Garth is just going to move through quickly here to refresh where we were at. But the what we're going to see, and Garth, if you can just... It worked just fine for me when we did, and that's 462.5.
Yep. We're going to recreate it real quick.
Garth's going to move through here, but as he loads this feed water, just note the temperature range here in the upper right corner.
25.
Oh, Garth, I had 5 there as the minimum before, but maybe that's... I had 5. That way we could actually just set minimum. All right, Garth's stepping through it. So we're going to see a 5 and 10, and then if you can bump that to 10 and go to 0.9.
Okay, 25 there.
All right, I think we forgot to set our run length. So if you want to jump back and set that to 24 hours. You're getting to see a lot of the interactiveness of Wave, but also how quickly you can move once you know what you want to do. So if
you'd say there's a 24-hour run length, we got a potential run time of 24 hours.
And if you want to just show that pressure drop again.
12.26 was the pressure drop.
So if you go up to
warnings.
That box and click minimum, I think that would be a good...
Right. So now it says 5.
Mm-hmm. And if you click refresh...
It took the same exact design.
Okay.
You told it you want to run for 24, but notice that the potential run time is shorter than that because there's a reduction in capacity as the temperature went down. And your pressure drop went up to 20. So.
Okay, so that's actually just over the threshold that we were wanting for this design. So something that I do in this scenario, or I've done, so one is, this is a nice feature if you have a design in a pretty broad temperature range to quickly evaluate the conditions at the different temperatures. So we could also go to the maximum now if we are curious about the max, but this also gives you a glimpse at projected throughput for a given temperature within a set design that you've just set. Yep. But one thing I'll note is when you do make that change up there, if you go back and make changes in Wave, it will refresh the design at the temperature that you set up there. So Garth, if you don't mind setting us back to the design temperature. And then I just want to go back to the feed water page and just give folks a tip of one approach that I do in this scenario, because Wave by nature is going to try to design a tall, thin vessel, which is ideal for ion exchange. But in some cases where you have a low temperature, a very low temperature, you might run into a scenario where your pressure drop is a little higher than you'd want at that low temperature. So in this case, just for the sake of example, I might take the design temperature and drop it to that minimum, or, and that's what I think we should do here, but another way to do it might be to bring that design temperature a little closer to the minimum so that you're not going to exceed whatever threshold you have set for yourself. But if we want to just step forward by setting that design temperature at 5, then we can do the same thing in terms of evaluating our design at different temperatures once we get to the summary report. But
okay, so I've changed the design temperature to 5. The water is now on charge balance because as we change the temperature, we change all the equilibrium constants. So the carbonate bicarbonate CO2 balance is no longer charge balance. So normally, since you were already charge balance and all you did was change temperature, all you really need to do is adjust the pH to re-equilibrate everything at the new temperature. So notice we changed adjust pH, and the pH here changed from 8.1 at 25 to 8.3 at 5. At this point, you can just hit summary report again. It'll rerun the design. It's now designed for 5 degrees C. So we solved the problem of having the capacity change. So we actually increased the amount of resin in order to give me a runtime of 24 hours at 5 at the minimum temperature. If we come down here and you look at your delta P at 5, it's 17, so that's under your 20 limit. And we got rid of all the warnings. So this design at 5 clears all the warnings. And then you could, as you said, check what happens at other temperatures. If you go all the way up to the extreme of 35 and just refresh the report, you asked for 24, you can actually go up to as much as 28 hours. Your pressure drop will come down as you get warmer, so no problems with pressure drop. And no design warnings. So we now have a system that has no design warnings at the minimum and maximum temperature. So at this point, you have a pretty good design.
All right, thank you, Garth. And just for if you're wondering what happened there is when it designed at that lower temperature, initially our vessel diameter got larger. So that's where we got the lower pressure drop.
Mm-hmm.
So, all right, thank you. And I think while we're on this example, we wanted to go back and look at the flow configuration options just to flesh that out a bit for folks.
Sure. So let's go back to our 25-degree design, and
just
obviously I changed temperature. I got to adjust the pH again and make sure this says design, so it actually designs. So now we have our base case for 25 degrees again. And you wanted to look at what happens with the train configuration. The easiest way to see the different options here is let's start with a 2-in-1 design. And we'll go run our summary report. And we'll take a little look at the detailed report.
Garth, we did get a little feedback that we're moving quick. So if we just take our time a little more with pushing the buttons.
Mm-hmm. Okay. So we're in the detailed report, and I'll blow it up as wide as I can get on my screen by clicking the little zoom button here to blow it up. And now we'll go look at the detailed report. And at the top of the detailed report is this little diagram that shows the hydraulic balance for the entire system. And there's 2 sets of numbers to keep in track. The one on the outside, so here's our feed flow, waste flow down here, and over here is our product flow. These are the average flows that essentially the outside world would see. So coming in at 462, leaving at 442. Then the numbers in the center are for each train. In this case, we have 2 trains running in parallel, so we have 231 gallons per minute. Down here, we would take out any water that we needed for backwashing or the regeneration. Then that up here would give us the water mass balance that actually flows through the vessel. Subtract off the number down here is the product water for regeneration, and that gives you the net product flow per train. So this sort of W in the center is what's happening at the train level, and the 3 numbers on the outside are what's happening at the system level averaged over multiple cycles, as opposed to what's going on during the middle of a cycle. So if we take our 2+1 design and make this a 1-0 design, you see you have several options open up. One of which we can use that 462.5 that we had on the home page, and we'll use that as the vessel design. So now we run the report again and go to the detailed report. And blow it up. You can see that we now have here in the center 462.5 GPM as the flow actually going to the vessel. You can do the same sort of W to see here's the product water used for the regen. Here's the net product flow. And then these flows here are for the time when the system is running. But we only have a single train, so there's also some period of time when we're doing regenerations and there is no flow. So the average flows on the outside will be lower because they take into account the off time. So the system produces 443 GPM when it's running of net flow, but if you average and include all the dead time, you actually only get about 395 GPM of product flow. Average. However, the other thing you could do is you could specify that you want to use that 462 as the daily average flow rate. So we do the same thing and go to the detailed report. Go to the report. Enlarge it. Now you can see that our system feed over here is the 462. And you also see an increase in flow rate because this is the flow when it's actually running through the system. And you get your W again. So we have 419 going through the vessel. We get a net product when the trains are running of about 497. Taking into account the dead time, you have 443. So one of the things that's one of the powers of Wave is you can actually specify the flow for many different places in the system. So,
Okay, so Garth, actually a good question that came in is what will happen if they change the water they're using for regeneration? And the design example, I just noticed that I think that we had product water selected. And the question is, what will happen if they use feed water for regeneration? That might be something that we want to just look at briefly to show the impact on, especially while we're in this flow rate examination.
Sure. So I guess we'll make it, you can see both effects. So you can select here which water you want to use for either feed water or treated water, both for the backwash and then the chemical dilution water. So I think we'll just split the two waters so you can see both of them, the impact. Since I'm running this design again, the final parameter screen here, if it shows up, means it's going to use the numbers from the previous run. 99% of the time, if you change an input, it will clear the final parameter screen, which makes it sure that you're getting a new design for your new conditions. So usually just make sure that this final parameter that shows here disappears. So if we run what you just suggested, okay, so now you could see, Matt, for example, we're using a lot of backwash water. So we had 462 as the flow. We get about 519 when you take into account the dead time and what's actually going to go. In this case, about 15 is used for backwash, leaves me 504 net feed to the cation vessel. Subtract off the waters used for the regeneration, gives me the net product water, the 497. If you want to confirm, a lot of these numbers are actually also in the tables below. So for example, the design flow rate of 504, that is the flow rate that the vessel actually saw. And then if we scroll down a little further, there's sort of a water balance table, which essentially shows similar information that was in the diagram. So we started with 462. The average is 462 coming in. We take out 19 as regeneration water, gives me a net product of 443. For the train, when it's running, the water consumption is 519, and you get 497 from the train when it's running. And if you check just below, here's your loading cycle and your complete cycle. And you can double check the math, but this volume of water going to the two flow rates is just the 2 times here.
Okay. All right. So,
Matt,
yeah, go ahead, Donna.
sorry, there was another question that came in. I didn't know if you wanted to take that now.
Yeah, I think that's a good one. The brine question.
Yeah, and there's also when to choose between a SAC sodium form and wax sodium form softening.
Yeah. Okay. So in terms, I think let's go to Garth. Let's go back to the design.
Okay.
And let's. There are a couple other things that we wanted to look at. You just gave a good overview of the whole train configuration piece, which just shows how much you can do in these different configurations if you wanted to run a single vessel or multiple vessels, looking at different ways of operating them. For the next couple of things, could we just jump back to a 1 online, 1 in standby? And I think let's just show how the specific velocity piece of the design works. And so I noticed we were right around 15 BVs an hour, I think, on our design.
Sure.
If we want to, go ahead, Garth. What were you going to say?
Yeah. So, right, when you pick length of operating cycle, Wave will essentially say, I'm going to run for 24 hours. I have this ionic load. It estimates the capacity and uses that to figure out the resin volume. If you specify the specific velocity, that essentially forces the resin volume, and then it tries to estimate what the run length will be. So it's 2 different ways of getting your design, specifying run length or resin velocity. So if we specify a velocity of 20 BVs an hour and run the report, you'll notice that your estimated runtime is about 17 hours instead of the 24 we had when we specified the time. And the reason is, as you mentioned, the specific velocity now is specified at 20. Before it was 15.
Okay. Now, if you go back up, so that's one way to approach it. And sometimes just when doing a new design, if I'm not given a run length requirement, I'll start with a spatial velocity design and see what type of throughput I get to, or what type of estimated runtime I get to for an ideal hydraulic set point. And then I'll work from there. So in this case, seeing we have 17 hours at 20 BVs an hour, I might lean toward that 24-hour design just because that's a common request. Or I might go to another even hour run length back in that initialization page. But you could see at the top here, system recovery of 95.8. Do we want to just go back? We can answer a regen question and take a look at maybe one of the features. You talked about how our backwash water was relatively high. I think we could just look at, before we get to the advanced page, can we touch on regen conditions, Garth? Someone asked a question about how to specify their own brine, and I think it's worth just showing folks. We don't have to do a whole one, but just maybe show them how they can do that from this page, and then we can move to the advanced.
Sure. I mean, if you wanted to check some concentration other than 10%, you would just enter the number here. So 8%, a little more dilute. For the same pounds or grams of dose, lower concentration gives you more solution. A higher concentration would use less solution. So, but right here is where you can change the concentration of brine you're using. The default is 10.
Mm-hmm. Okay, and then, but I think this question was specifically about adding a different bulk concentration.
Different bulk concentration. Okay. Okay, so 26% brine is essentially saturated brine. If you wanted to specify something else, what you could do is you could go to your user settings and go to the chemical library, and you have a list of chemicals that are in here, including sodium chloride at 26%. So if you wanted to add a chemical, you could add sodium chloride, and the default concentration is 26%, but if you wanted to say you had 24%, you would enter 24% there. Since we know about sodium chloride and its density curve, it will give you the new density. You can estimate a price, and you would now have a new entry in your drop-down list. So if I add the chemical, it's added successfully. And now if we exit out of everything, we now have the original system 26% and you're 24%. Yeah. So now you select that one, and it would run the design using your chemical, not the system chemical.
All right, so I think let's go back to our 26, and then let's jump to the advanced regen page. And two things that we can look at is, one, how we might be able to impact the backwash water, or the amount of backwash water, or the expansion. And another question that came up that's a good one is that sometimes the person that submitted this, Kurti, submitted a question about getting a warning for specific velocity during regeneration. Basically, when he gets to the end result, the specific velocity for the regenerate is not within limits, and he's just asking for some tips on how to fix that.
Okay, so sure. A lot of the details about how the regeneration are performed are on this advanced regeneration condition page. They're all filled with defaults, so normally that's a pretty good place to start. But if you want to get into the regeneration in detail, you could come to this screen. So the first three entries have to do with backwash. The backwash expansion is a crucial number because WAVE will look at the temperature of the water and the degree of requested expansion to figure out what linear velocity of water is required, and then uses the diameter of the vessel to figure out what flow rate of backwash water is required. So as I change, if I were to run this at 100% expansion, I have to expand the bed more. I need more water. It's a higher flow rate. That's more backwash water. Conversely, if I were to reduce this to 60%, less expansion, lower linear velocity, lower consumption of backwash water. So expansion essentially controls the linear velocity that's going to be used for backwash, and then the duration obviously is how long you backwash for. So depending on your TSS load and how much stuff you need that builds up on the top of your bed you need to get rid of, you can vary the backwash duration up or down depending on your TSS load. So if you were to put 30 minutes in there, you'd use half as much water for backwash.
So let's just do that, and then I think we should maybe drop that to 30 and the backwash to 60, just so we can show the impact on recovery.
Sure.
And then
we'll
just
get back to the SV.
Yep. And then just to touch on Kurti's question, there is an option in this page to adjust the regeneration specific velocity. The default value is generally going to be within the range of what would be considered acceptable. Sometimes in a mixed bed, you may the two specific velocities are contingent upon one another, and you could change one to maybe impact the other, and it may be that you have to interact with those dynamics that we're not necessarily going to be able to look at in this example, but it is one way to try to address that.
I have one that we should be able to see that coming up, an example of that.
Yep.
All right. And speaking of that, Garth, we should probably move through the end of this. If you want to get to the summary report, Donna is still on the line,
we want to
folks.
get to my example, okay?
Yeah.
Okay, so the last thing that I just want to show here is, and Garth, maybe, how are you doing?
Yeah, I'm here.
Just okay. So if you're able to get to the summary report, maybe we could do that. And we've changed so many things that I don't actually know. If you go to the IXOFT page and the
Which
initialization, go to the initialization. Let's just see what our we're at 20 BVs an hour. Okay, let's just move on. And let's let you start Donna's example. But if you go to the feed water page, there's just one last thing I want to comment. Because it's something that happens with some frequency as you go through a design, either you missed this notation, or you send out your design and you get the feedback immediately after that 462, I'm sorry, not feed water, but the home screen. You get some feedback that 462.5 GPM was actually supposed to be the product water as opposed to the feed water requirement. I did just want to show that with Wave, you can just jump over to this bullet point, change the product water to 462.5, and then run through, and basically the design will refresh, and it will potentially change, but you could follow that same process and just quickly change the product water, and without too many things changing in terms of the setup of the design, you could do that. So I think we should wrap it up here and let you move on to Donna's example.
Okay. Hi, Donna.
Hi everyone. My example today, what I wanted to demonstrate was how to optimize on your anion system. So the example that we're going to be looking at is the Mississippi River water. So often a design request will come in, simple SAC SBA, but people are open to optimizing around that to see what the best configuration may be, maybe adding in a WBA or just looking at the strong base anion itself. So Garth, can you run an example for us? So we're not going to worry about fine tuning all the design. I just want to evaluate this river water and how we work our way from looking at just a simple SAC SBA and moving through something where we're adding in a weak base, and then we're optimizing the overrun on that to see what kind of effects we have and how we can save resin volume and also, in some cases, chemical and water. So can you start with the simple SAC SBA on Mississippi River water?
Okay,
which is high in alkalinity.
What flow rate would you like?
800 GPM is what the request came in for.
800. Okay.
Yeah.
So we'll get out of our water library. The Mississippi River is a fairly typical water quality. I believe you told me that this had been filtered, so the TSS is nowhere near that high.
Yes, it's gonna filtered and drop, but everything else is going to be pretty much the same. The alkalinity and the we're not going to. I want to focus our efforts on the anion, and so I'm not going to worry about fine tuning the SAC first, but so let's start with the SAC SBA.
Okay. So we go here. What kind of run length do you want?
24 hours, please.
And I'll assume we'll do a 1+1 design.
Mm-hmm.
Okay. And you would like a SAC SBA design. Co-current?
Yep.
Okay. Resins 1200, 4200.
4,200.
Okay. Regeneration. You were using sulfuric acid, I believe.
Yep. Sulfuric acid and caustic. And the nice thing about the sulfuric acid, Wave will give you recommended concentrations to use based on the amount of calcium in the feed. So I usually go with what Wave recommends there. Yeah,
there's one other thing let me put in. Some people notice that there's actually a maximum contact time of acid with the resin because of the calcium content, and you want to get it out of there before it precipitates. So if you use sulfuric acid, it will put in a fairly large specific velocity that will be calcium dependent, and you're not going to really be able to go below that.
That's a good point.
Okay, so just note that actually, the default, if you were using something other than, if you use hydrochloric acid, this is like 3.5 BVs an hour. Okay, so I believe your specification for conductivity was 10 and 20. And Wave taken the conductivity, we'll estimate what the sodium concentration that corresponds to that.
Yeah, and they're going to be using a mixed bit after this, so don't need to get that conductivity.
Okay. And what kind of doses would you like to look at?
I think let's do 9.
And for your SBA?
Yeah, let's keep that one around 9 as well.
Okay. Okay, so we have our design. Get 24-hour runtime.
And it's a huge.
Probably a good size.
Yep. So It is. Let's see if we add, since this is Mississippi River water with a high alkalinity, let's see if adding the degas in will help us.
Sure. So we'll go back to the demineralizer. That's on the vessel page. And we can put in a degasifier. And you can confirm it's in there. It'll show up in your diagram. So we can now rerun the report. Same 24 hours. And we got rid of half of the anion resin by putting in the degasifier.
Okay, great. So now if I want to reduce that even further, and especially the amount of chemicals that I'm using, I'd like to see what happens when we add in a weak base anion. So could you please take us through adding in, let's use HPR 9500.
Okay, so we're going to change the regeneration system. So you want to go to a weak base, strong base. So you would click here. You'll get a warning once you start changing the configuration. Many of the entries on lower screens get changed, either cleared or set to default limits. So you're going to want to step through everything just to make sure that nothing's changed. So we have 3 vessels, all concurrent. Let's put our degasifier back in. It hid the diagram because it's now too big for the space. The resin, we wanted 1200, 4200 for the strong resins, and you said 9500 for the weak base, I believe.
Yes.
Regeneration, we'll go with the sulfuric acid and caustic again. This was 10, 20, that was 9.
And I wanted to take a moment just to talk about what we're looking at here with the different options for overrun and the regeneration ratio. And so I usually start at 115% of regeneration ratio, and that is with respect to the anion loading on there, the amount of chemical for that total anion loading. And so I start my designs with 115%. And you'll notice there's another option there for percent overrun. And also at the bottom of the screen, there's an automatic and a manual button, if you can point that out, Garth. First, I just wanted, for the purposes of the demonstration, I wanted to start just with the manual and a 0% overrun to show people what wave is going to be predicting for them.
Okay, so okay.
Now,
so.
I don't know if anyone noticed it originally in the feed. We took it. There's a large amount of alkalinity, and when we took that out, that reduced a lot of the anion loading. And what we're left with is a very large amount of strong acids from the free mineral acidity, and a very small amount of the weak acids, now silica. And so if you do not have any overrun, wave, will try to, balance that, the amount of anion resin, the weak base to handle the strong acids, and the strong base volume to handle the weak acids, silica, and whatever is going to be coming out of the degasifier. So the bicarbonate coming out of there. And so if you were to look at this volume here, can we scroll down to see what we have? And do we have any warnings?
So, okay, so we have 317 cubic feet of the weak base resin and only 97 cubic feet of the strong base resin. So there's a huge excess by volume of strong base, weak base resin. And you can see here we have a overrun of 0.
Mm-hmm.
The dose, we have 115% regeneration ratio for the 2 resins, given the 97 cubic feet of anion resin. That worked out to be a dose of about 10 pounds per cubic foot. Nice high dose.
Mm-hmm. Mm-hmm.
If we scroll all the way down to the bottom, you see that we actually tripped several warnings. And if you look at the warnings, the first one, the specific velocity is too low for the second resin. And if you think about how we did the regeneration, we specify that we want a certain flow for the strong base resin. And now I have 3 times as much weak base resin,
mm-hmm.
so the specific velocity is 3 times higher.
Right.
Which means, or 1/3 as high. Sorry, I have 3 times as much resin. I have 1/3 as less of velocity. So that's the reason for this warning. So the way to clear that warning is
well, before we clear the regen warning, I wanted to talk about just the whole imbalance of the system and letting wave do the automatic run.
Okay.
And so now, clearly we don't want to go with this system. It's not optimized. We're getting errors on our flows because of the imbalance in the resin volume. So can you let wave do its thing, let it do its automatic, and let's see the optimization, and let's talk about that and see what the results are before we change anything else.
Okay.
On this one.
Change the order we fix things.
Yeah.
So now we're going to put in automatic overrun. And what this wave will now do is overrun the weak base resin. So some of the ions that are normally removed by the weak base resin are allowed to break through the weak base resin and will get absorbed by the strong base resin. That allows the weak base resin volume to come down a little and the strong base resin volume to go up. So we're going to essentially trade off between the 2 resin volumes. So in this particular case, Wave's automatic solution brought the weak base down and added 10% more to the strong base volume, took it from 97 to 107.
And how does WAVE choose what is the optimum here? What's the criteria that it's looking at to say this is the volume that I want, the ratio?
So there are many things you could use to define optimum. Which WAVE is using right now is minimizing the resin volume. So it's going to add up the weak base and strong base volume for each overrun it checks, and it's going to look for the minimum in that curve.
Okay.
Okay. In this particular design, it didn't do much overrun. It only did about 5% overrun.
Okay. Okay. So if we were looking for the smallest resin volume, then using the WAVE automatic would help us out. And were there any errors in that?
Yes. We cleared the SV warning on the resin loading. We're left with the regeneration SV warning. Mm-hmm. And this is the one I was starting to talk about.
Right. This is the one that we got a question earlier on about trying to clear the error when there's a specific velocity with regard to the regen.
Right. So in this case, we have two resins. They're being regenerated thoroughfare, which means the regenerant goes through the strong-based resin and then through the weak-based resin. The flow rate's being set by the strong-based resin, which means it's too fast for the weak base. So what we're going to do is, sorry, it's too slow. We're going to go adjust the flow rate. And we go to our advanced regeneration screen. The specific velocity right now is 3.5 BVs an hour through the strong base, and it's about a third of that through the weak base. Mm-hmm. So in order to get the velocity through the weak base higher, I'll also need to increase the velocity through the strong base. So let's take this up to about 5. Now we can rerun the report. And now we see we actually got a different overrun answer, and we cleared the warnings.
Great. Thank you, Garth. Now, as you mentioned, there's other reasons why you may want to optimize on. And so I just wanted to talk about running a percent overrun ladder. And in order to save time, I wanted to, we prepared in advance a table of what that ladder looks like. And we created this by using the manual run. And so as you can see, as you scroll, as you increase your percent overrun, and we're looking at 115% in this case, regen ratio. As you increase your overrun, you're increasing your strong base anion resin and decreasing your weak base anion. But when do you know you've gone too far, and when do you know it's optimum? Well, the criteria that you might want to look at here is percent silica loading on the resin. If you have too little overrun, you might be putting too much loading of silica. When you run to a break, we have a recommended silica loading, and you might cause precipitation issues, so you want to keep track of that. Also, your organic loading. You don't want to have so much overrun onto the strong base that you don't have enough weak base anion. We have a recommended loading of organics per cycle, and if you exceed that, then that can cause you issues. And then also the amount of caustic that's loading on the strong base anion resin. We have recommendations there as well. And so you want to keep track, if you're doing a ladder and fine-tuning, as to where the sweet spot is going to be depending on your situation. And it's going to be different for different waters. So Garth, let's see if we took a look at this one. If the total anion loading, having the smallest amount, was not necessarily our goal here, and we wanted to maybe optimize more on balancing organics and some other things here, and getting like maybe the lowest silica. If we expect we might have very variable silica, in our feed, then it looks like maybe somewhere around between 30 and 40% might be a good spot, to look at. So you can run a ladder like this and evaluate further.
So in order to do that, you would go back to your product quality page, and instead of having automatic here, you would switch it to manual, and you would put in, say, 35% as your overrun, and just run the report. So you could, if you don't want the automatic solution, you can use the manual one, and it will run the design. 35% overrun. Slight, our resin volume has gone up from the optimum that Wave found.
Mm-hmm.
We still have no design warnings.
Garth, I got a question from someone about, they were asking a question of why, like when they have lower percent overrun, their silica, no matter how much, silica is in there, it seems to be 12 grams of silica per liter of resin. Maybe looking at
Sure.
that first example, you can explain why that may be.
Right.
And they keep getting that.
I just want to give you, Garth and Donna, a heads up. We are coming to the top of the hour. We can decide whether to keep going or
I think we
want to wrap up, but go ahead.
I think we'll take a couple of questions.
Mm-hmm.
This one and maybe one or two others.
Right.
One of the things Wave is doing, and it gets into how it determines how much resin you need. Normally, it's going to be basing it on the operating capacity and the ionic load, targeting your safety factor of 0.95. If you have a large amount of silica, it's not going to let you run to a capacity endpoint. It's going to run to a silica endpoint. So it would run, it would set the resin volume not on capacity, but on silica. So in this case, we have a limit of 12 grams per liter. This particular example was 5.9. If we change the conditions, the silica number could come up, but it would not be allowed to go over 12. So if this number and this number are the same, you have a silica limited design. And one of the ways you can know it, besides these two numbers are the same, is the safety factor will no longer equal your target. It'll give a lower safety factor because your design was limited by silica, not total capacity. Okay.
Thank you.
So,
All right.
Any other quick questions before we wrap up?
Garth, this one lines up with something we wanted to show in another example. How do I load a file from a coworker?
Okay. If someone sends you a file, you can go to File and open and save our projects you created on your own system. Import and export are used to send files to a colleague, and then you would import it. So if you click on Import, we're not going to save this project. You then pick where you have the file, and we could then load in a specific file, and it would add it to your system.
Okay.
So,
all right.
So
that's nice. All right. Anything else, Donna, you want to pull in? As we're getting to the top of the hour, we want to say thanks to everyone for joining. I'll do an official wrap up when we're ready, but.
We did have that one question about the weak acid cation.
Oh, yeah. So we did. Yeah, we did a sodium form softener. Generally, things to think about when deciding between, a question came in about using a sodium form strong acid cation versus a sodium form weak acid cation. And generally, the decision point comes from TDS level. The higher the TDS, and generally what we would classify as high TDS streams, or when you would think about using a sodium form weak acid cation resin. But things to just be aware of, it's not the same as running a sodium form strong acid cation resin. The process of running a sodium form WAC includes an acid regeneration as well as typically caustic for conversion to the sodium form, as compared to strong cation is converted using sodium chloride. So it's not generally not the same cases that you're considering one versus the other, unless it's borderline, but or maybe there's additional factors, but at a high level, those are some things to think about.
And which TDS would you use to flip between them? You have a rule of thumb?
I think we generally would maybe start evaluating it. In addition to TDS, I guess it's hardness to total TDS level. So I don't know if I have a specific number that I would give off the top of my head. But Donna, I don't know if you have one that you would maybe just give.
No, I don't either.
All right. So anything else we want to touch on real quick? Okay, so we are getting more questions, and people are still on the line. Do you want to drop your screen, Garth, so people can see it? No, I just someone's asking about thoroughfare regeneration of a DI plant containing weak base anion resin and strong base anion resins. Essentially, wave is that's relevant to the example that you were just talking about. And someone's also asking about the use of low resin volume versus optimal overrun percent and factoring in chemical consumption. I don't know, Donna, that table that you showed kind of worked through some of that information. Do you have any additional comment on that question?
On the thoroughfare regeneration one?
Thoroughfare, and then balancing the optimal overrun and cost of chemical.
So first for the thoroughfare regeneration, I do want to make a comment on that. One, having the weak base anion resin, you regenerate this with the spent regenerant from the strong base anion. And one of the things to be careful is sending a silica front over to the weak base anion, which is going to have lower pH because it has all the mineral acidity. So considerations would be for something like that is dumping the first third or so of the spent regenerant, so you're not sending that silica front into a low pH zone. Or you could decrease the concentration of the caustic a bit. We have some other recommendations for that. So it's mostly to avoid precipitation. So that is something to be aware of. Also, what was the second question, Matt? I didn't see
that was about.
Oh, the chemical?
Yeah, resin volume versus optimal overrun versus chemical consumption, and ultimately, chemical consumption relating to cost and balancing that.
Yeah, so I think creating a ladder like we did, I don't know, Garth, if you want to pull that up. I don't know if you can share that.
So, yeah, we'll show the entire screen again. One thing to remember when you're doing a weak base, strong base couple is we specified the regeneration not as a pounds per cubic foot. We specified it as a stoichiometric ratio relative to the ionic load. So actually what happens is the quantity of chemical is constant. Every one of those ladder points use the exact same amount of caustic. We just changed how much strong base and weak base resin that chemical was applied to. So as you increase the strong base volume, you end up with a lower dose of pounds per cubic foot because I have more cubic feet of resin, but I still have the same fixed number of pounds of caustic.
Mm-hmm. And you can change by increasing the ratio. You know, if you wanted to use more chemical, you can up that to 125%. Our range was 115, 130%.
It's fairly typical.
Yeah,
right. And I think that was
fairly typical. Mm-hmm.
That was a good explanation. So thank you. So Garth, if you want to bring us back to the cameras and we could just say goodbye to everyone.
Sure. Okay. So,
go ahead, Garth. Any comments you want to make?
Well, thank you, everybody, for joining our webinar today on ION Exchange. I hope you were able to learn some of the features of Wave that are not necessarily obvious to those who haven't played with it as much as the team has. And feel free to ask any more questions you have of your presenters, and we'll get back to you as soon as we can. Thank you all very much.
All right, Donna, anything you want to say?
Yeah, thanks for your time today. I was really excited about participating, and please feel free to send in your wave scenarios that you would like us to evaluate, so we have examples for our future wave webinars.
All right, thank you, everyone. Thanks a lot for being here. We appreciate it. And you know, the webinar series continues. We have more wave webinars coming up, but the next webinar that we want to let you know about is next week. Catalysis is the topic, and our close colleague, Jose Antonio, will be the presenter, and he supports these applications in North America and South America. So we're excited for that, and hope you get a chance to join.
Thanks to Bill and Matt, too. I mean, Bill and Mark.
Yeah, thanks.
Mark Clark and Bill Carlin for answering the questions while we were online.
And bringing some to us. So thanks a lot. Appreciate it.
Okay.
All right, bye, everyone.
Bye, everyone.
Bye-bye.
Bye-bye.